Hi, today I'm going to talk about the solutions for Atcoder Beginner Contest 402 problems A to F. And for problem A, we have a string consisting of uppercase and lowercase English letters, and we need to print out the string that's obtained by concatenating all the uppercase letters in S. And so for this problem, we can directly do this by using a for loop and looping through all the characters in S and checking whether each character is an uppercase or lowercase letter. If it's an uppercase letter, we can add it into our answer string, and in the end, we can print out the answer string. And we can look at the code. So for this part, I looped through my string, and then I checked whether each character is an uppercase or lowercase. So this part, I'm checking if it's not a lowercase. Then I will add it to the answer string, and I'll put it at the end. And next, let's look at problem B. And so problem B, we have a waiting line in front of the Atcoder restaurant. And initially the waiting line is empty, and each person would join the line and would have a meal ticket that has a number on the dish. So we need to process Q queries, and then there are two types. One is given in 1x, which means that one person would join the end of the waiting line, and then they would have a menu number of x. And for 2, we need to print out the person at the front of the waiting line, because that person would be guided into the restaurant. And so for this problem, we can use the data structure of a queue, since a queue can simulate the process of waiting in line, since it is first in, first out, which is exactly the process that is going on here. And let's look at the code for how to implement this. So for this part, we have the queue here called line, and then for each query, if it's a type 1 query, we would input the number x and then push it into the queue, since this means that one person joined the waiting line, and so our queue will have one more number. And if it's the other type of query, then we will print out the number at the front of the queue, and then we will pop it out, since this means that it's removing the current person from the front of the queue. And next, we can look at problem C. For problem C, there are n types of ingredients numbered from 1 to n, and the restaurant offers dishes numbered from 1 to n, and each dish uses ki type of ingredients, which are ai1 to aiki, and Snoop currently dislikes all n ingredients, and he cannot eat any dish that uses one or more ingredients he dislikes. But however, he can eat a dish that uses none of the disliked ingredients, and over the next n days, he will overcome his dislike of one ingredient per day. So he will overcome his dislikes in the order of BI, given by the list B, and so on day I, he will overcome his dislike for ingredient BI. And afterwards, if a dish no longer includes any of his disliked ingredients, then that dish can be eaten. And we need to output the number of dishes that can be eaten after he overcomes his dislike of ingredient BI for each of the I from 1 to n. And this can be done by storing a map of the ingredient number to the list of dishes that need the ingredient. So we do this because when Snook overcomes his dislike for each of the ingredients, we need to update the value for all the dishes that need the ingredient. So we would want a method to keep track of the ingredients and map it to the list of dishes that need that ingredient. And since we want to know whether each dish still contains some ingredients that are disliked by Snook, we will want to keep track of a count I that stores for each dish I how many ingredients are still disliked and those ingredients that are needed by dish I. And after we store these two values, we can loop through B again, which is the order that Snook overcomes his dislike for the ingredients, and then we can subtract the count for each dish that requires the ingredient. So what this means is that for each ingredient, we can loop through the list of dishes that need the ingredient. And then for each dish in this list, we can loop through the count for each of the dishes and then subtract it by 1, because this means that these dishes now have now use one less ingredient that Snook dislikes because he just overcame his dislike of the current ingredient. And so if the count becomes 0, then this means that the current dish that we're checking no longer uses any of the ingredients that are disliked by Snook. And then so now he can eat this dish, and then we can add 1 to answer because that means that there is one more dish that he can eat. And so if this is still not clear, we can look at the code. So this part, my unordered map C represents the list that I mentioned about mapping the ingredient number to the list of dishes that need the current ingredient. So this part is taking in the input, and I'm creating my list I. So for each dish, it requires K ingredients, and the K ingredients are given by A. And so for each ingredient A, CA represents the list of dishes that require ingredient A. So dish I will require ingredient A, and so we push that into the vector CA. And count I, as I mentioned, represents the number of ingredients needed by dish I and are currently disliked by Snook. And since initially Snook dislikes all n ingredients and dish I requires k ingredients, then that means that Snook would initially dislike k ingredients that are needed by dish I. And then we loop through the order that Snook overcomes his dislike of the ingredients. So for each ingredient B is the ingredient that he currently stops disliking. And so we loop through. This is V represents all the dishes, the current dish that uses ingredient B. And that's what we stored in CB or earlier when we processed the inputs. And we subtract count V by 1 because this means that there is one less ingredient that Snook dislikes. And so dish V has one less ingredient that it can't use. And so if count V is equal to 0, then that means that dish V no longer includes any of the ingredients that Snook dislikes. And we can update answer by 1 because there's one more dish that Snook can eat. And then for each ingredient, we output the answer. Next, we look at problem D. So for problem D, there are n equally spaced points on a circle labeled clockwise as 1 to n. And then we have m lines where the ith line passes through the two distinct points AI and BI. And we want to find the number of pairs of lines such that the ith line and jth lines intersect. And so we can look at the sample input. And so we realize that one thing to notice to be careful of is that the lines are not chords, so they can also intersect with each other outside of the circle. So for example, in this case, the line that passes through the points 1, 8 also intersects with the line that passes through 2, 4. And so a key point to note is that any two lines that are not parallel will intersect with each other. So we can convert all lines into the form 1 to k. So what I mean by this is that, for example, the line 2, 4 is parallel to line 1, 5. So we can treat them as equal because they are parallel. And so it is important to note that we can treat all parallel lines as the same line, but just update the counts of how many lines that are parallel. So since 2, 4 would intersect with all of the lines that would intersect with 1, 5. So we can convert 2, 4 into something into 1, 5 to make it easier to keep track. And so after we convert all of the lines into the form 1k, and which again is that it is a line that passes through the point 1 and some other point k, which is in the range 2 to n. So this would represent all possible lines, since 1, 2 can represent lines 3, 8 or 7, 4 and also 6, 5. So the lines from 1, 2, 1, 3 to 1, 8 would represent all of the possible lines. And Since only the parallel lines won't intersect with each other, we need to keep track of the number of lines that are parallel to 1k after we transform all the lines into the form 1k. So count k can just store the number of lines that are parallel to line 1k, and then so after we transform each line, we can update count k, and afterwards we can loop through all of the lines, so all m lines, and for each line we can update the answer like this, which is the total number of lines subtracted by the number of lines that are parallel to the current line. So if we look at an example for this, what I mean here is that if we're looking at line 1-8 according to the sample input 1, then m will be equal to 3, whereas count k will be equal to 1, and the 1 just represents line 1-8. Like line 1-8 itself, since there are no other lines that are parallel to line 1-8. And so this gives two lines which are just 1-5 and 2-4 because they are not parallel to line 1-8, so they will intersect with line 1-8 eventually. So there will definitely be some point that will intersect with line 1-8. And so we can do this for all other lines and update the answer by subtracting the total by the number of lines that are parallel. And in the end, we will need to divide the answer by 2 because each intersection will be counted by both lines. And let's look at the code for the specific implementation. So we first take the input of the lines, and then new b is just the k that I mentioned previously, and then so I update this by transforming it by adding ai minus 1, and then so I do this because, for example, if we want to transform the line 2-4 into 1-8, we want to subtract 2 by 1 and add 1 to 4. So then I just added ai minus 1, and then this is just the amount to transform a to 1, and then we add that onto b. And so this would be our new value. And however, since our numbers are numbered from 1 to n, we want to ensure that the numbers don't exceed that range, so we can take the remainder when divided by n. And then so if new b is equal to 0, since our numbers are from 1 to n, we don't want the 0, so we can set the 0 equal to n. And so the count I mentioned is the number of lines that are parallel to line 1k. And so afterwards, after we transform each line, we can add count new b to add 1 to count new b, because this means that there's one more line that is parallel to line 1k. And then this part we loop through all of the m lines and then update the answer according to what I just mentioned, which is adding all m lines and then subtracting the lines that are parallel to the current line. And at the end, we divided the answer by 2 because each of the intersections would be counted by both lines. Next, we look at problem E. And so for problem E, in the year 30XX, each submission to a certain context requires a payment, and the contest has n problems, and problem I has Si points, and each submission costs Ci yen. And Takahashi submits the ith problem. He solves it with a probability of pi%, and each submission's outcome is independent of the others. So he only has X yen, and he doesn't want to make any submissions that would cause his spending to exceed the X amount of money that he has. And we want to find the expected value of the total score when he chooses submissions to maximize this value. And so even if he submits any problem more than once, he is only awarded the score once. So even if he gets one problem correct many times, it only counts as once. And so since n is small, it's just 8, we can think of bit mask dynamic programming, since in this case we would want to keep track of which problem that he has gotten correct, and also the remaining amount of money that he has. And so this problem is like a knapsack dynamic programming and also a bitmask dynamic programming, and we can represent the DP states as dpij, where I is a bitmask that represents which questions are correct. So this would be maximum 2 to the power of 8, and then J is the amount of money that is currently left. And so this maximum is 256, and then there's 5,000 maximum to the money, so then this satisfies the memory constraints. And as for the transition for each state dpij, this comes from, first, this part is if there's pk probability, where k is what we loop through and is the current problem that he submits. So if there's pk probability that he gets the kth problem correct, and if so, it will add sk to his total points, and it will come from the state dp I minus this part is like the bit mask that doesn't contain k. So when the kth digit of the bit mask is 0, which represents the state that the current state just without the kth question correct. And this part, j minus ck, I think j should be the amount of money that has already been used. Yes, sorry for that mistake, but J should represent the amount of money that has already been used in this current state. So, when we loop through the current submission, this will come from J minus CK since an additional CK amount of money is used in this current submission. And this part is if we get the current question wrong. So if we get the kth question that we're working on wrong, then this occurs with a probability of 1 minus pk. And this would come from a state of dpi since there's no transition to this bit mask because we don't get problem k correct. So we don't have to transfer from what we did previously from I minus 1 to the power of k to I. So we don't need to do that, and this state will just be I. And then, however, even if we get the problem wrong, we still need to pay a CK amount of money to make the submission. So this will come from the amount J minus CK, since now previously we only spent J minus CK amount of money, but then now we spend J. So let's look at how to implement this. And so we first get all the inputs, and then we divide pi by 100.0 because p is given in percentage and we want it to be decimal points. And this part we loop through the dp states and then perform the dp transition. And so I is the bit mask that represents the current questions that we already got correct, and J is the amount of money that we used. And this part we loop through the current question that we're trying to submit. And this needs to be a question that is included in I, and we can check if both if the kth digit of I is equal to 1, and this means that I includes the question k. And we need to check this because we're transitioning from a part of the transition is from not getting the question correct to getting the current question correct. So it needs to be from some question that's already included in I. And this part is the dp transition that I mentioned previously. So the first part is if we get the current question correct, which occurs with pk probability. And the second part is if we don't get the question correct, which occurs with 1 minus pk probability. And then as for how to calculate the answer, we want to find the maximum of all possible combinations of questions that give the total score. And then we have a maximum amount of money x. And so this part we loop through all the possible combinations of questions that we get correct. And we find the maximum of dpix because x is the maximum amount of money that we have. And we print it to 8 decimal points or more because the problem requires a precision of 10 to the power of 6, negative 6. And next, let's look at problem F. And so problem F, we have an n times n grid, and each cell ij contains a digit from 1 to 9, and cell ij contains the digit aij. And there's a token at the cell 1 1, and we need to move it either for each operation. We need to either move the token down or to the right, and then we need to write out the sequence of digits that we visit in order. And we need to find, if we see the sequence of digits as an integer, we want to find the remainder when this integer is divided by m. And we need to find the maximum possible score when this integer is divided by m. And so we notice that n is 20, and this hints that the problem is likely related to bit mask. And so for this problem, we cannot simply brute force, because this would take too long, since it would be equal to choosing n minus 1 from 2n minus 2, because there are n minus 1 steps to the right and n minus 1 steps down, and we need to choose the order of n minus 1 from these 2n minus 2. And so instead, we can use a meet in the middle operation. And since we want to look at the string after we walk from cell 1 1 to cell n, we want to see the string as an integer. We can first transform each cell aij into aij times 10 to the power of 2n minus I and minus j, and then in my code I used ij starting from 1. And since we want to perform meet in the middle, since this would reduce the time complexity, since we would only need to check a path from 1 1 to the middle k n plus 1 minus k, and another path from n to k n plus 1 minus k. And so we can store the sums to move from 1 1 to this point, and the sum to move from the end back to the middle, into two separate vectors that are s1k and s2k separately. So this would store the possible sums to move from 1 1 to this point, and we can store it into s1k. And so after we have the two separate arrays, one moving from the start to the middle and the other from the end to the middle, we can find the maximum total sum through binary search. And we can look at specifically how to do this in the code. And so this is what I did in my code. And I first transformed aij into what I mentioned, which is multiplied by 10 to the power of 2 times n minus I minus j. And so one thing to be careful of is that we need to use long, and also we need to make sure to modulo m after each operation to avoid overflowing. And this part is calculating the sum from the start to the middle, and then this section is calculating the sum from the end to the middle. And so from the start to the middle, we loop through there's n-1 steps, and we do this as a bit mask where 1 represents a increase in x and a 0 represents a increase in y. And we can add as we loop through all possible combinations, we can keep track of the sum of the current path that we're in. So we can add axy into the sum. And then so since when we reach the middle, we still need to add the middle value into the sum. And then for this part, when we're looping back from the end to the middle, we won't add the middle value to avoid the middle value being overcounted. And so we push it back into the array S1x, which keeps track of the sums when we move from the beginning to the middle. And this part is doing the exact same thing, but then just changed it to move from the end to the middle. And what I mentioned about performing binary search is that we can sort for each I from 1 to n, we can sort S1I and S2I. And S1 is what I mentioned about the sum from the beginning to the middle, and S2 is the sum from the end to the middle. And for each value in S1, we can perform binary search. So we can find the value that is less than m minus v1. And so because we want to find the maximum sum modulo m. So for the maximum sum, we will want the other value to be just less than m minus v1. And so if we can update the answer only when j is not equal to begin. And that way we can subtract 1 because we want less than and not and lower bound gives us greater or equal to. And so we can update the answer to find the maximum. And then another way we can check the maximum is if we add the current value with the largest value from the end to the middle, so the largest value in S2I. And so we can find the maximum of all of these values, and at the end, we output the answer. And thank you for listening.